pretty. Cool. Okay, team. So these are the various things that you've discovered about the shapes using the PhET simulation. I've also passed out this summary table that I got from the ESA textbook. This is honestly the best summary table that I've seen. So something to keep in mind is that these are all the shapes and all the bond angles. This will not be given to you on the assessment. What did I just say? This is not going to be given to you on the assessment as a resource sheet because you have to memorize it. Oh. So this table here that I've kindly decided to spend my printing budget on is for you guys to help you memorize. It's pretty logical when you think about it, so let me walk you guys through it so that way we can make sure we understand shapes. So what you guys have realized about shapes is that the shape of the molecule is determined by the center atom. So whatever's in the center, we're doing stuff as reference to that. There are going to be a couple of questions that are going to be a little bit different from that, and I want to show it to you guys. I think it's either in the CPR quiz or it's in the example that I wanted to choose for you guys. I can't remember which one. The second thing is that lone pairs, you've realized, affect the bond angle. So the thing to keep in mind is that when we are looking at our molecules, you have the lone pairs of electrons which are unbonded, such as this one here. You also have bonded electrons which are between two atoms. Now something to keep in mind is that these are all electron negative. Or regions of electron negativity. So what that means is that they're all negative regions. And what we know previously is that like charges repel. They do not like being next to each other. So they're going to repel, and what they're going to do is they're going to repel so that way they have the maximum distance apart from each other, because that minimizes the amount of energy. So that's why when you guys are playing with the PhET software, and every time you added something, either it be lone pair or bonded, it then changes what you're dealing with. It starts shifting everybody so that way they can again maximize the distance they can have in that current situation. The other thing that you guys were looking at, and I'm going to jump down, is as you add to the center atom, the bond angles get smaller. And that makes sense because now you still have the same area of space that you're dealing with. So now that I added another lone pair of electrons, I now need to move things to maximize their separation in that situation. And when you guys are moving around these little electrons, these atoms, you'll notice that it will temporarily make them closer. But when you let go, it then goes to the maximum distance that it can be allowed. So that's what you're looking at for that. Let's go back to our list. So we figured that out. Bond angles are also only between atoms. So if you guys are looking at this, we notice that we are measuring the bond angle between these two atoms. We are not concerned about the lone pairs of electrons. So that's something else to keep in mind. The other thing you guys have noted is that the double and triple bonds get treated as one region of electron negativity. So for example, let's just delete that guy, delete that guy, delete that guy. So actually, no, we'll do that. Keep it like that. So we see how this is 180. I've added a double bond, but it's not being added as two separate bonds because those electrons are being shared together. And so it's just treated as one region, exactly the same as if I had added a single, a single atom. Okay? Are we all right with all of that information? Or do we have any questions? Okay. Cool. So let me walk you through this sheet here, and we'll use the simulation to help us make sure that we know everybody. And then I'll show you guys an exam question. I probably won't do a whole lot of writing for this. I'll see how you guys go and what you want. I'm also mindful of time. All right. So this, like I said, is the best way I've seen this organized. As a table. So what we have here is we have a list of things. This first list here, so this column here and this column here, is referring to the regions of electron density. So it doesn't matter if it's bonded or unbonded, we're just saying how many total do we have. So in this case, we're dealing with 4. In this case, we're dealing with 3. In this case, we're dealing with 2. So when you guys are looking at these guys here, you see how, in this case, when I have 4 things bonded, it says tetrahedral electron geometry. So this is what we're referring to. If I delete this and I add it as a lone pair, it still has the tetrahedral in regards to the electron in regards to the regions of electron density. The other thing you guys will notice is that the bond angles here have not changed between the atoms. 109.5, 109.5 still. So it doesn't matter if it's an electron lone pair or if it's bonded electrons, it's still going to influence the angle the same way. So if I wanted to delete two of these and put two lone pairs, again, we're back to tetrahedral for our geometry for the electron, and then the bond angle between these two atoms is 109.5. So when we're looking at this summary list here, we'll see that all of these bond angles are being referred to as 109. Now, it drives me a little bit bonkers that they're saying 109 because mathematically it's actually 101 and 109.5, but if you wrote 109 on the exam, they still accept it. Are we okay with that? Okay, the next thing that is then going to get asked is, okay, what is the shape of the molecule? So the shape of the molecule is only influenced by bonded atoms. So any lone pairs doesn't actually get drawn in the three-dimensional shape. So when we look at this guy over here, you see how we have this molecule shape is bent. If I remove a lone pair of electrons and add in a single bonded electron, I have the same bond angles, but now the shape goes to triagonal pyramid. And the reason why it's called that is because it looks like a pyramid. See? And then the other one was called bent because it looks like it's a bent shape. Like that. All right, if I get rid of those two and add my two bonded electrons, now it's tetrahedral. So that's what it's referring to when we're talking about this bit here. Okay. The last bit, now we're starting to look at what happens when we have fewer regions of electron density and how does that influence shape. So let's get rid of one. So this one here is 3 bonded regions. All of them are bonded electrons and no lone pairs. Now that I have one less region of electron density, I've now increased my bond angle and I have 120. Are we okay with that? We notice that this is electron geometry-wise triagonal planar, and then molecular geometry-wise, we call that triagonal planar. If I replaced one of those with a lone pair instead, it's still geometry-wise the same bond angle, but now we have a bent shape. Something to keep in mind is that there are two things that are bent shapes with different bond angles. They love, love, love to ask that as an exam question because it's a good compare and contrast. How could two molecules have the same shape but different bond angles? It all has to do with the fact that there's an extra pair of lone electrons. And lone pairs of electrons affect the shape, affect the bond angle, but are not counted in the shape. So you see? Take that away, bond angle gets a bit bigger, add it in, gets squished. Still the bent shape though. Yep. So often on the exam, they like to ask molecules that are bent in 2 different ways. They'll ask you, how can you have a bent molecule with 2 different bond angles? The reason is that both molecules have 3 atoms with 2 bonded to the center. The difference is how many lone pairs of electrons they have. So lone pairs of electrons affect the bond angle, but do not change the shape because they're not counted in the shape. So it's just a nice compare and contrast. So this one has 4 regions of electron density, 2 lone pairs. This one only has 3 regions of electron density, 1 lone pair, but the shape is the same because they're 3 atoms. So they love, love, love that question. All right. And then the last one that we have is our linear shape, which is this one here. So in this case, we are just talking, technically the single bonded one is also, but we're dealing with that one too. So that one's just linear, it's straight chain, like that. All right, the moment I start adding electrons to it, it's starting to go to bent. And if I have that, which is like carbon dioxide, again, it's still, there you go, no, it's still 180. All right, so those are your different shapes. They usually make sense with what you're describing. In this case, it's linear because it's straight. The other one was the bent ones we talked about. The triagonal planar is like the pyramid, except it's flat. Planar means flat. If I add the lone pairs of electrons, I now shift everybody down, and that's why it's now a pyramid. So the shapes are pretty logical. I know you guys have to memorize it, but it's pretty logical. All right. What did I want to add? I think that's more or less it. I'm just seeing if there's anything I want to note on here on a piece of paper. I don't think so. Is there anything you guys want me to write down? Are we okay? All right. Let me show you the exam questions that I was thinking about. Did I grab an exam question? No, I didn't. Interesting that I didn't do it. Okay. So there's a really good SciPad page that goes comparing the shapes and the bond angles. It does give a scaffolded answer of what the different layers are. So what you need to be mindful of is Lewis structure is crucial, because if you get the Lewis structure wrong, it snowballs and you get the wrong shape. When they ask this question, they often ask you to compare and contrast bond angle and shapes. Be mindful of how you are layering your answer. I would personally start with bond angle. And then go on to shape, because the bond angles is just referring to how many regions of electron density you have, versus shape is how many of those are then bonded and unbonded. So that's how I would be layering my answer. Make sure you're talking about both molecules. Make sure you're also adding comparison words. So like I said, they often do things that are very similar. So you'd be like, although they both have 3 atoms, they have different bond angles because, and you have to go through each step. One of the things you're going to be definitely using is VSEPR theory, which is explaining how these regions of electron density are going to separate for maximum distance apart to minimize repulsion. All right? Could you repeat that again? Yeah. Do you want me to write that down? Okay. Just watching your time. All right. So when we are talking about these things here, the 4, the 3, the 2, and all the bond angles that are occurring, we are thinking about how these shapes or these bond angles are arising because of VSEPR. And I can't remember what that acronym actually stands for. Let's see. I've always just referred to it as VSEPR. VSEPR. There we go. Valence shell electron pair repulsion theory. That's what that stands for. What it's basically doing is trying to predict 3D shape. So with the VSEPR theory, what we're stating is that the result of the bond angle and the shape is because the regions of electron density are trying to separate for maximum distance to minimize repulsion. So when we say electron density, we're talking both about bonded and unbonded electrons. Maximize distance to minimize repulsion. The other thing that I want to, you guys have the 3D shapes already drawn for you guys in the notes, which is good. That's why I really like this example. That's the other thing I want to talk to you guys, because I know Nadira was stressing about how do I draw this information, which I'll show you. Sorry, I wrote that too fast and now it looks really messy. So VSEPR, the regions of electron density separate to maximize distance to minimize repulsion. It's the lowest energy state these molecules exist at. Who's coming? All right, keep going. Okay. So, Nadira, you were talking about 3D shape and how do we communicate 3D shape on a 2D plane? All right, they have it here. So often on these exams, they will ask you to draw the Lewis structure and they will ask you to draw the 3D shape. This here is the Lewis structure, showing the dot diagram. This here is the 3D shape. So one thing to keep in mind is that in the 3D shape, you do not have the electrons being shown. Okay? The other thing that we indicate is how do we indicate 3-dimensional shape? So we need to think past molecules.
It's a body one thing where what they're supposed to be like. Clever. I don't know.
So this is my tetrahedral. This is 3-dimensional shape. Yeah? 3D shape. We're trying to communicate this 3D shape in a 2D plane. So the way we do that is we got to think about the plane of existence. So let's imagine that the line for the plane of existence is right here, going through the center. like that. All right. So in my 3D shape, there are 2 items that are within that plane. One item is going out of the plane and one item is behind the plane. This is the plane. So when I'm drawing that, the single lines refer to within the plane. The bolded line means coming at you, and the dashed line means behind you.
Wait, also you just love to have a.
So I'm just trying to communicate 3 dimensions. Yeah, so you're just saying, here's my shape, here's my molecule. Let me zoom it out so you guys can see more things. All right, here's my piece of paper. So this thing and this, these are both within the plane of the piece of paper. Because if my imaginary paper was still going through it, it would be within the plane. So that's the single lines. This one is coming out at you. It's in front of the plane, and we communicate that with the bold line. So like a triangle that's filled in. And then this one is behind the plane. So this is my plane. This is behind the reference point. So we draw that as a dashed line or a dashed triangle. So that's how we're communicating 3-dimensional shape. Now, when you're drawing this, the trick is you basically need to have 2 that are the same plane and then 2 of the other 2. So if you want, you could have shown it like that, and you could have shown it like 2 things coming out at you, one within the plane and one behind the plane. That's also correct. You need 2 of one and then 1 of the other 2. All right? Sorry, that's awful. This one here is I've removed 1. So this is a lone pair of electrons right here, but I cannot see it. So it's influenced in shape. So I'm not drawing those lone pairs of electrons. I'm still trying to communicate 3D shape. So again, when I go to draw it, I have 1 within the plane, 1 coming out, 1 behind. And so that's why you have a bold line, a dashed line, and a normal line. All right. And then this guy is that guy. This one, you have no dashed or bolded lines because this one can exist within the plane. It's flat. This is 2D now. All right. So sorry, guys. I can tell you're like, I hate this. Let me show you guys the planar. All right. This one's planar. So you saw how you had the pyramid, right? Yep, nice. Okay, this is the planar one, so this is this guy. So this one's also, nope, lied. Flat.
Can you draw it on the whiteboard?
What do you mean draw?
What it would look like?
I can draw it on a piece of paper. Want me to just draw it on a piece of paper, that way it's recorded? Right, so if I was trying to draw what I just had before, the methane, I would draw my carbon. I would draw 2 single lines with the hydrogen to state they are within the plane. I would draw that as a triangle, bolded, to represent the hydrogen coming out. And then you can either do a dashed line or you can do like a dashed triangle, doesn't really matter, to represent the hydrogen that's behind.
And the one that's colored with that triangle is
Coming out at you. Okay?
so the imaginary paper type of thing would be going.
So the imaginary paper is going this way. And then this is coming out of the paper, this one. And this one is going behind the paper. Now, dash line is to represent behind, bold lines to represent. Yes, it's flat. We're talking about 2D. We're trying to communicate 3 dimensions in 2D plane. It's really hard. All right. So we saw the pyramid, right? When I was talking about the pyramid, do you want me to go back to the pyramid? Yeah. So here's my pyramid. Yeah, 3-dimensional shape. So when I draw that one, it would be nitrogen. This one would be within the, so if this is where it is and the paper's on the ground, so let's say the paper's going right here.
Yeah.
So one's within the plane, one's coming at me, one's going behind the piece of paper. That's how I communicate that one.
Let's dig a hole in the paper.
Well, through the paper next time I could. Just bring in some Play-Doh to the assessment and just show them what you're trying to communicate. Yeah. Anyway, I do want to show you guys the planar shape for the 3 bonds. So in this case here, you see how it doesn't have a lone pair of electrons? So now this guy lays flat.
Wait, that does or doesn't have a.
Doesn't have a lone pair because you see how it's laying flat, and this is 120. So when I go to draw this, because this is laying flat now, this would happen with, for example, the boron. You can just draw it the same as your Lewis structure because it's all flat.
Oh, yeah.
It's that guy there. And then when you have the bent shapes, you can draw those flat as well because those can lay flat on the same plane. And same thing with this guy.
It's so only when you have.
It's only when you have the triagonal pyramid and the tetrahedral that you have to worry about drawing it like that. So that's the good news. It's not too many of them like that. All right, those are our shapes. I do want to point out the CPR question, just so you guys can see a yucky example. Oh, that's to refresh properly. I put the no brain too small as well because you can start doing those questions. Term 4, week 1. So you have the holidays to study. My friend Leanne does have on his website, so you have the Lewis structure diagrams. You also can do SH, which is shapes. So shape of the diagram. Sorry, drawing of the diagram, shape, because he's giving you the Lewis structures. So you can do the same practice. Cool. And then if you refresh it, it changes the questions. And this one now actually gives you an exam style question too, where you actually have to write an answer. All right, let me show you the CPR quiz because I just want to show you guys something in case it comes up and I don't want you guys to be thrown off by it. I have seen it actually on the exam. It is from a mock, I think this one. But I don't want you to freak out. Okay. Every so often, they like to give you a nasty molecule like this. And now you're like, where the hell is the center? I don't want you to freak out because you see how they label things as A, B, and C. So you're treating this as the center for that section. So each one of these sections have their own bond angle and shape. So they're just asking you in reference to each one. So this one, A, has 1, 2, 3 regions of electron density. So you figured out what the bond angle and the shape would be for 3 regions. This one here has 1, 2, 3, 4 because you're looking at B now, which is where that carbon is. And then this one here is looking at the nitrogen. You have 1, 2, 3 regions of electron density. You also have to be mindful that you would have a lone pair of electrons there.
What's the point of the other one, which is very low?
They just, yeah, they're making it harder than they need to. This was from a mock exam, which are more challenging, but I feel like I've seen this on the exam questions as well, so it is actually something that will come up. Let me just pull up the exam questions and see. So you see they've already started to do on some of them. I think it was more recent. I haven't seen it on the older exams, but you see how that one is like pain in the butt. It's bigger. Let me find the exam questions. Level 2 chemistry exam. Because I remember looking at it on the exam and thinking, that's not very nice. I think it was a more recent thing they started doing, which I didn't think was cool because like you guys had COVID and I was like, why are you doing this in the COVID years when everything's harder? I think because they're worried that the exams are too repetitive, so they want to throw in a curveball.
But then it's unfair to the
I know. All right, let me see. I think I saw it on the recent exams, and that's why I wasn't too happy about that. Yeah, so you see they're giving you a bigger molecule, and they're asking you, okay, what's the bond angle for the carbons, and what's the bond angle for the oxygens? So it's like, why are you giving unnecessarily big atoms? This one wasn't too bad.
Wait, could you go back up to that one?
Yeah, just scrolling through to make sure I didn't miss anything. Yeah.
Where did you start on that? Because that's not me.
So in this case, they say just the carbon atoms. Both of these carbon atoms have 4 bonds to it. 1, 2, 3, 4, 1, 2, 3, 4. So they're both going to take the same shape. And they're both all attached to atoms. There's no lone pairs. There's only 1 oxygen there. Now you see again, they have the same bond angles, but they have different shapes. So that's again an example of the compare and contrast. How do they have the same bond angle but different shapes? How do they have the same shape but different bond angles? Very common. Let me find you. I thought I saw it on one of the exams, and I was like, you guys are not friendly people. See if I can find it. All I know is I was not happy with it, and I was like, that is not fair. Maybe it's not on that one. I could have swore I saw it. Maybe I'm wrong. Anyway, it's worth just, I'll give it to you guys on the CPR just so you guys can see it in case it does come up. They haven't been as hard as the one on the CPR, which is good. Link. Oh yeah, this is the one that was already on the, all right, so yeah, it just seems like it was just on the, yeah, mostly those are pretty straightforward. All right. Cool. Maybe I missaw something. Maybe I'm confusing it with another one. But anyway, just in case they do something crazy like that, that's what it's referring to. Okay? Questions, concerns, or comments?
No.
No questions, concerns, or comments. Is what I'm taking that as. Okay.